All right, thanks, Randy. Good morning, everybody. Anybody that knows me knows I tend to be a procrastinator when it comes to putting talks together, but I'm usually a really successful procrastinator. In this case, we got our second largest ever October snowfall yesterday for the Twin Cities for at least one day period. And we got records at St. Cloud and Eau Claire. So the combination of that and having a 2-year-old, which I never had in the past, made me a little less of a successful procrastinator. So there's some things that I wanted to throw into here that I'd hoped I could get done last night or this morning, but that did not occur. So there's a few things I left out, but that's fine. You'll get an idea of what they would have been. I'll try to speak to some of that and at least give you some context for some of the additional work and things that we're looking at. So before I jump into this, I did want to at least quickly refer back to some of what Andy just talked about with respect to the events he looked at, given that we just had this big event yesterday. It's one event, so it pretty much means nothing, but it was encouraging looking at the GEFS output going into the event we had yesterday in comparison to the previous version of the GEFS, which although we'd looked at, we'd really had very little confidence in it. Whereas this event yesterday, it did pretty darn well. I've archived off a lot of the probabilities and other stuff, so I'm probably going to go back and maybe share some of that to you, Andy, just to look back, because I know as many as like 3 or 4 days, it was doing pretty well in both the probability values and the corridor that it was highlighting for some of the higher amounts. So that was encouraging, but of course, it's only one event. The other thing Andy mentioned was, when you're looking at some events to kind of put them in a context of climatology and what's historically reasonable. And we certainly were doing that, which was part of the reason yesterday we kind of had an advisory going for a long period of time. Part of that was uncertainty, but part of it was we would basically be forecasting kind of a record event to go a little bit higher in accumulations and bump up an area into a warning. We eventually did do that yesterday, just considered impacts even without regard to the amounts. And of course, it turns out we got a record event. So, that's just one of those little caveats. It's definitely something we think about and something we should think about, but record events do happen. So with that, now I'll actually jump into what I was supposed to be talking about today, which is snow ratios, which also obviously came into play yesterday. So I'm going to kind of just give a brief overview of, snow ratios, what we do with them at the FO. Obviously, everybody on this call is pretty familiar with that. A very brief overview of just snow ratio climatology, kind of what we look at and what we have looked at over the years in terms of what we have available to us. And then I'll kind of dig in a little details of what we've been trying to look at locally in terms of maybe getting some improved knowledge of how our snow ratios vary, at least in our specific geographic area and for our location. So we'll look at some of the, the data we used and how, how I looked at that and so forth. I do want to give a shout out also to Bill Borgoff and Chris O'Brien from our office. They helped me with some of this work, so I do appreciate some of their additional assistance in this. And then, of course, as always, I'll just kind of talk about all the things that I haven't done yet that I still need to get done for this. So everybody's pretty familiar here in the Central Region. Most offices, I think, or at least probably half or more, do 6-hour snow ratio grids, which has its benefits and its negatives. In the short term, which is when we're really trying to get the amounts and the values for snowfall nailed as best we can, there tends to be a little more freedom in what we have available to us and how the snow ratios get populated and how they get updated. And obviously that has to do with how we handle our forecast collaboration process. And thankfully, we've got folks working hard at that again in the ESTF prototype and experiment. And, I'm sure we'll see some improvement there over time as well. Forecast Builder, as we know, gives us kind of a common starting point for those grids for the period over which it runs. So that's a good thing in terms of at least all starting with the same general idea and then modifying from there. But the thing to keep in mind, of course, is the actual snow amount that falls out of our grids is kind of brought together by that combination of the QPF, the pot grids we generate, and those pot grids, of course, depend on a number of factors in and of themselves. And it also depends on some foundation grids, like Andy's email that he just sent out a couple days ago about how the temperature and the dew point together making up the wet bulb when you consider the topography. Those also come into play in terms of whether snow actually is allowed to accumulate in the grids, because we kind of have hard threshold values for temperature and wet bulb where accumulation isn't necessarily going to be allowed to happen in the grids. So those things, and then snow ratio is one additional knob that we are allowed to turn, so to speak, in the FO. So, in my mind, and this is just going to be my personal, cynical opinion, we've got an awful lot of degrees of freedom that are involved in forecasting snow amount, and snow ratio being one of those for which we have, some data, some observed data over the years. I would just argue against spinning too many knobs at once when we're going through this process if we can help it, because a lot of times you are wrong in 3 different things and you wind up being right for obviously the wrong reasons. But it's best to kind of stick to what you have some confidence in when you're turning those values. So that was kind of some of the justification behind looking at this and kind of getting a sense of what reasonable values are. And then kind of some of the future work would be more of a predictive fashion in terms of trying to get a better idea of how to predict these ratios. Snow ratio climatology, I think everybody is pretty darn familiar with kind of the seminal work that we use in terms of knowing what our local climatologies are that Marty Baxter, Chuck Graves, and Jim Moore did years ago. I'll just link to that real quickly. Whoops, that's actually the paper. I didn't want the paper. I want the website. Here we go. From SIPS, where you can actually just kind of view this stuff from that paper that was done years ago. And one of the big things they pointed out was, if you're just to look at the country as a whole, kind of a 13-to-1 average is sort of what came out as a climatological snow ratio value that was sort of better if you would just look at the whole country together versus kind of that historical 10-to-1. And if you mouse over your given forecast area, here's us for the Twin Cities. It kind of showed our average was about 13.5 from their study, with the median being slightly less, down at 12.5. And you move around. If I go out more toward Rapid City, I'm going to have higher values of snow ratio as you get more into the high terrain and some of the colder areas versus near the coasts. And here's where obviously that 10-to-1 came from, because we all know everything of meaning comes out of the Northeast corridor in the Mid-Atlantic. So it's no wonder, obviously, we kind of use that 10-to-1. So some of the things to keep in mind, though, with that study that was done years ago is they wanted the highest quality data they could work with in terms of both observed snowfall and the actual liquid precipitation values. So they utilized our co-op network, which is pretty much our highest quality data that we have a long record of for those things. And there's good and bad to that. Obviously, the big positive is, in general, the data quality is pretty darn good. It makes it a little easier to QC and throw out some of the bad data when you do find it. But a big negative from us, from an operational perspective, is it's for the most part 24-hour data. So obviously over a 24-hour period, you're going to have things like compaction come into play, melting come into play, and other things that could negatively bias that perhaps towards some lower values than what we may typically observe or think that we observe. So that's a big caveat there. So one of the things we were looking at is, well, we're forecasting these 6-hour snow ratio amounts. That's kind of what we do. It would be awfully nice if we had some sense of what our 6-hour climatology might be, for our area. So, oops, there we go. And so for us, what I did is I took the data from our office. We've been here for a while, as have most of the offices since the mid-90s. And for the most part, folks have been taking 6-hour snow measurements and getting liquid equivalent as well, whether it be from the 8-inch gauge, taking cores of the snowfall with a 4-inch gauge and melting it down, or doing both depending on the situation. I think most FOs make a pretty darn good effort to come up with the best liquid equivalent they can for those 6-hour amounts, but realizing that there is still error, whether it's due to strong winds during the period or whether it's due to melting that occurred at the beginning or end. So there are still some of those data QC issues that come into play, even with the data from the WFOs. But for our purposes, I think I would hope that most of us would think the data from our own offices is some of the higher quality data that we have available. So for us, what was available is 1997 through 2019. Obviously now I have last winter, which I didn't include in this because I did a lot of this work last fall prior to COVID turning us all for a loop. But I at least had the data up through 2019. And I only looked at the cases where we had 6-hour snowfall amounts of 1 inch or more, just to kind of weed out a lot of the sort of crazy ratios that you may end up with in some of those really light snowfall cases, whether it's because you simply can't get any liquid equivalent or the snow melts, et cetera. So And I did also, in terms of going through the data, when I kind of show some of these graphs later, some of the mixed precip cases, et cetera, are pulled out. Because luckily, when we take these obs and put them into our local spreadsheets, we do make sure we have notes in there of whether there was mixed precipitation, freezing rain, sleet, et cetera. So I was trying to focus mainly on just the cases that were purely snow, just so I have a better sense of how the ratios worked out. So the snow and liquid precip came from our office, and for the actual weather data, I took the hourly METAR data from our nearest site, which is an ASOS at Flying Cloud Airport in Eden Prairie, which is just the next town over from Chanhassen, where our office is. And kind of mentioned all this. The big thing there is obviously we have 6-hour amounts for snow and liquid equivalent. So hourly METARs were basically averaged over that corresponding 6-hour period during which the snowfall occurred. I did remove specials during that time just to make the math and the processing easier of the data. So it is just sort of those hourly values over the 6-hour period. And I pulled out the temperature, the dew point, the RH, average wind speed, and pressure. All of these are averages. They were obviously the hourly values, and then I averaged them together over that time frame. So took essentially the basic data that's available from a METAR. A lot of text on this slide, but this was basically sort of the summary stats for all of the cases. So over those 22 winters, there were 366 6-hour periods with an inch or more of snowfall. So that's essentially 2% of the possible periods that could have had an inch or more during those winter seasons. Only 6 of those periods actually had 6 inches or more of snowfall, but that makes sense because, you know, how often does your 6 inches actually fall exactly within a 6-hour period? So a lot of our 6+ inch cases would have, you know, spanned more than one observation period. So that makes sense. And then some of the oddities that do come from whether it's, you know, just inability to measure due to wind or all the other factors that come into play in a real world environment. You know, there were some interesting things. You know, 13% of the cases had exactly 1 inch measured. That's possible, I suppose, but it seems like, you know, maybe there was a little bit of averaging or rounding off that occurred there. And then 8% had that exact 10-to-1 ratio. You know, maybe not, but, you know, that could have been a little bit of estimation there. And then, you know, a whopping third almost of the cases had a ratio that wound up being a whole number versus, you know, instead of it being like 12.1 to 1, it was exactly 12 or exactly 11. So there might have been a little bit of estimation there as well. So not to say that even data from your own FO won't have some interesting artifacts in it, but for the most part, when I looked at the data and looked at the cases, it seemed reasonable. Some of it was thrown out. So this was sort of all of the cases. The analysis that I'll have some graphs for, I did get rid of some things that seemed suspicious for sure, just given some of the other factors and some of the nearby co-op observations and things like that. So unfortunately, when you do a study like this, it does become a little bit labor intensive in terms of the data QC. But the big thing here at the bottom of the slide is essentially 3/4 of the time of these cases, the ratios for us were between 10 and 25 to 1. So it kind of tells you, you know, you're only into that 25% of the time where you fell outside of those ranges. And you'll kind of see what the amounts were in those cases on some subsequent graphs. So just kind of giving similar numbers to what you kind of saw from the Baxter et al. Study. This is for all cases, so this is everything of an inch or more. The maximum ratio, which this got tossed out after I did some QC on the data, but this was prior to that being done, was 100 to 1. Once I did QC, I think the highest ratio that was left in the data set was about 43 to 1 in our case. I do know from working in Marquette for years that certainly some of those really extreme ratios are possible, and Dan in his next talk is going to talk about some of the meteorology that goes along with high snow ratio cases. But also for all of our cases, 90th percentile 30, but big thing here is the average was 17.1 with a median of 15 to 1, which both of those are a bit higher than what came out of the Baxter study, but not surprising because these are 6-hour values not done over that 24-hour period where compaction and melting and other things come into play. At least consistent with that study though, in all of these, the stats, the mean was always a bit higher than the median. So because that makes mathematical sense because on the low end, you're stuck at 0. You can't have a negative snow ratio. So mathematically one would expect the average to be a bit higher than the median, given that fact. If we look at just some of our more, say advisory type and better cases where we've got 3 inches or more of snowfall, essentially the numbers all are very similar. They just come down a little bit from what was in the previous slide. So instead of 17.1 to 1 for an average, it's 15.8 to 1, which is still a bit better than the 13 or so that was in the climatology from the Baxter et al. Study. So still kind of suggests a climatological average for us a little bit more than what we may have assumed, at least when we're doing it at a 6-hour time block, which is what we're doing when we're doing these things in GFE. So that is kind of important, something to keep in mind. But then that also factors into how we come up with storm totals in GFE, which I'm not going to get into details, but we all know there's issues associated with that of simply adding 6-hour amounts and coming up with a storm total, because obviously compaction and so forth occurs. But that's a whole nother thing to worry about. So some of the relationships in terms of comparing the ratios that we saw to some of those meteorological parameters. So I'm just going to step through several graphs here. These are all just for us here in Minneapolis, or for Chanhassen, I should say. And they're all essentially laid out the same way, where the snow ratio is always going to be on the y-axis, that snow liquid ratio. So you're kind of going from 0 to 1 all the way up to 60 to 1 in this case. And then along the bottom is whatever I'm comparing it with. So in this case, it's the actual observed snowfall. And I've also in all these graphs color-coded those snowfall amounts and sized them based on different bins. So you've got kind of a 1 inch to 1.9, a 2 to 2.9, 3 to 3.9, 4 to 4.9, and then just 5+ I just lumped in together. So this obviously, look at the R squared here, it's terrible. It's down at 0.005. But if anything here, not surprising. If you had a greater amount of snow in 6 inches, you tend to have a lower ratio. There is one good outlier there that has, like a 35 to 1 ratio. So that would be kind of one of these events that would be similar to what Dan Baumgart will kind of be showing in his presentation. But for the most part, you get to bigger snow events, the ratios tend to be lower. And we'll see a much more, a better slide that illustrates that here in a few seconds. So now some of the things we're used to looking at, and even back in the day when people took OBS, they would reference a chart that gave you a ratio for snow that you could use based on your surface temperature. And indeed, there is a relationship. And out of these basic meteorological parameters I used, this did have the best linear R squared value, and it's about 0.3. You can kind of see there in the upper right. So pretty much what we expect. At warmer temperatures, you're going to have a lower ratio. And you can kind of eyeball it here. I apologize for not marking off where the 32-degree line is, but you can kind of see when you get near 32, very few, if any, ratios are above 20, and most of them are definitely down at 15 to 1 or lower in our case. So to get those values of 20 or 30 to 1 to be a little more common, it looks like in our case we needed to be down in the 20s or even colder. But you can still see there's an awful lot of spread here. Even when we're down at between 5 and 10 degrees above Fahrenheit for our surface temperatures, our ratios are varying anywhere from 10 to 40 to 1. So you obviously cannot just use this one parameter in isolation and not consider other factors if you were trying to come up with a snow ratio. Looking at dew point shouldn't be too surprising. It obviously is going to mirror the temperature for the most part, because you're going to be pretty close to saturation in these cases when you're actually snowing. So pretty similar. R squared value is about the same. So nothing amazing to see here. Wind speed. Now this was one of the parameters that we know does play a role, because obviously if it's windy and you get drifting and fracturing of snow crystals, you're going to tend to knock down the ratios. Of course, those cases can also be the ones where getting an accurate measurement is more difficult. So not a great correlation here, but you do see at least what you would intuitively think, which is at higher wind speeds, it is difficult to get any of those higher ratios. So once again, anything better than 20 to 1 in our situation is pretty darn uncommon. Once our winds get above 12, 15 knots or so, it's pretty rare that we would see a ratio getting too high. So that, all of these things are just kind of things you would keep in mind if you're going through and you're doing the grids and looking at an upcoming event, and you're thinking, well, gee, look at these temperatures, look at these wind speeds that I've got. and I'm going with these, 28, 25, 30 to 1 ratios, it just kind of would be if nothing else, just a mental check of, bringing those kinds of things back to something that's probably more realistic. And then this was just versus pressure, which was mainly done just because I had the data and it was easy to compare with, but this is basically kind of just another way of looking at temperature for the most part, given that some of these higher values of altimeter or station pressure here are going to be some of our colder cases. So you have sort of an increasing ratio at higher pressure. So that's not too surprising. The next one here, though, is probably what I found to be the most telling or the most useful in terms of a heads up if you were doing the forecast. And this is a very simple, just comparing the ratios. So once again, the snow liquid ratios are on that y-axis. And then the 6-hour just precipitation. So that liquid equivalent is along the x. Now your R squared from a linear perspective is, a little bit less than it was for temperature, but if you do a log relationship, you get a much better value, close to 0.5 here. And just from the eyeball test, you can see, or at least I can infer, a lot more usable or meaningful information here, and basically setting kind of limits. And and in our case, you look here and you get to a half an inch or more of QPF in a 6-hour period, and your ratio for that same 6-hour period is essentially going to be 10 to 1 or less, or pretty darn close to it. And then just citing yesterday's Snowfall event as an example, pretty much all of our 3 main climate sites plus Chanhassen and Eau Claire were just a little bit less than 10 to 1 for the duration of the event, around 9.5 to 1. The airport, Minneapolis, was right at 10 to 1, and then St. Cloud was a little higher. They were closer to 12 to 1, but of course they were further north, so they would have been a little bit colder. So all of those kind of make sense, and also all of them were in that greater than an inch of QPF land. So just from a simple dumb guy meteorology perspective, if you're doing your grids and you've got, in our case, obviously this is where you'd have to look at each individual FO, but for us, you're getting up over a half an inch in your 6-hour QPF grid. Well, you probably shouldn't be putting in a snow ratio that's much more than 10 to 1, and certainly not 15 to 1 or higher. And if you had just put in climatology, you would have been higher in that case. So that is something to kind of consider. And then if you kind of look at the left side of this graph here, you just kind of see, the lighter QPF amounts are sort of the higher ratios. And part of that is those lighter QPF events are colder. That certainly comes into play, but also you're going to have less compaction with less liquid and just, less weight essentially in the snowpack there. So you're going to just naturally tend to have a higher ratio in those cases. So this is sort of the big slide, and the main thing that kind of got me thinking of, okay, I need to look at this more. We need to take more things into account, and I need to look at data from additional places. And that's some of the stuff I was hoping to get in here, at least a few slides, but the world intervened, and I wasn't able to get some additional material in there because I just didn't have a chance to do the full QC. But kind of here is what I said with the only real surprise at all is that relationship of the snow ratio to just the amount of precipitation during the corresponding 6-hour period. And as I mentioned, there are some definite physical reasons for that, with compaction being pretty obvious. If there's more liquid in what's falling, it's going to weigh more, it's going to tend to result in more compaction. So it almost does place a physical limit on how high that ratio can be, depending upon the amount of water that content is in that snow. So that is it can serve as a quick check to make sure you don't have some unreasonably high snow ratio value in your grids. The other results were previous to similar findings. And the big thing there is just you've got a lot of variation. So with nothing else to consider and all things on the table, it in my opinion, which is kind of this first bullet at the bottom under opinion, so happens, is straying significantly from climatology without some good scientific justification can often be foolhardy. And there's 2 reasons for that. One is the obvious amount of spread you could see just based on those basic meteorological variables. And the other is what I referred to way back at the beginning of the talk, which is we've already got all these other knobs that we can turn in GFE that can affect our resulting snow amount. And I guarantee, you might be able to play around with the snow ratio and increase it by 5 or decrease it by 5, but in a lot of those cases, you might miss the QPF by a factor of 1.5 or 2. So, you're going to have error in other places, and it just seems to me silly to introduce additional potential error unless you have, some good reason. And that's kind of will be nice where Dan follows this up and will give you some good examples of when you would have scientific justification for going with some higher ratios at least. And then that simple QPF argument I made can kind of help you knock down ratios, obviously, in addition to the warmer temperatures. Just having high QPF cases could do that. So the last bullet there I kind of already referred to, but just, it kind of speaks to what that last graph said, where in our particular case, we didn't have any cases with more than a 0.3 of an inch of precip in 6 hours that had a snow ratio of greater than 17:1, or basically greater than our climatology. So some of the future stuff that I'm currently doing is right now I'm also, I got data, thankfully, from a bunch of, pretty much all of my surrounding WFOs have sent me their 6-hour snowfall and precip data, and I'm just working to get those correlated with the best nearby METAR observations I can do. And I've completed a couple. I know Patrick up in Duluth has been clamoring for me to get him the data, and I basically have it done, but I wanted to run through some additional QC, which is why I didn't put his in here, because his was the other data that I could have included right now in here. The big thing is I'm just trying to find a way to script or streamline that process as much as I can, because it's still a little bit data intensive. But for the folks that have sent me data, I am going to be working to get that to you here probably over the next few weeks to a month. So anybody, if you sent me data, you should have some at least basic results similar to what I showed in this presentation in your inbox by the end of November at the latest. The one other thing I'm doing here with MPX data is we are a co-located upper air site, so that does allow me to do at least an attempt at looking sort of at the three-dimensional profile and compare that with our snow ratios. And for that, what I'm pulling out of the upper air data, I'm trying to keep it as simple as I can, but also look at some of those key factors that we as meteorologists, sort of look at. One is just that coldest saturated temperature at or below 500, and that kind of correlates with what's, often gets referred to as a Kuchera or the Air Force method, which sort of looks at a coldest temperature within the profile. Just also looking at the saturated layer depth at or below 500 millibars, and then I'm kind of looking at the saturated layer depth between -12 and -18, which would correspond in general with what we often consider as that dendritic snow growth layer. And then a real poor man's tool here, just because we're using observed sounding data, looking at the wind direction change in that same layer as a real simple inference of whether or not you might have some forcing in terms of if you had veering winds through that layer, that would imply warm advection and some vertical motion in that same layer. Also looking at the depth of the -4 to -6 layer, which corresponds with kind of where you have rime splintering occurring. So you would get sort of that ice multiplication, which can, also potentially increase your amounts. And an often forgotten layer, that 0 to -3 layer, which is actually a secondary dendritic growth layer. So that's some of the data that I'm pulling out of our upper air sounding data. You can imagine some of this can be automated, but so far I haven't yet scripted a way to do this, so it's still a lot of manual labor. I've got about half of our data set done, and this is just a look at a spreadsheet where I kind of have those columns with those different variables that I just referred to. And another additional factor that comes into play with the upper air data is we're looking at 6-hour snow ratios, but of course our soundings are 12 hours apart, so I'm having to do some weighted averages where, weighting the soundings that are closer to the 6-hour period. So if the snow occurred between 0 and 6Z, the 0Z sounding would get more weight than the 12Z sounding because it was obviously closer to the time period during which it occurred. So some further work, in addition to finishing that data for my surrounding sites and working on our upper air, is, what to do with all this once we have all the data. I can look at these simple correlations like we saw in these graphs and at least pull out some somewhat meaningful information from a forecast perspective. But if we wanted to look at it in any way of a predictive fashion, that's where I'll need to go in and kind of do some multiple linear regression, perhaps logistic regression, so that we could kind of break up into probabilities of ratios exceeding certain levels throughout the distribution. And then if I could find somebody who certainly knows more about it than I do, because it's not something I've delved with too much, would be kind of trying to put some of the data into sort of a neural network setup and see if we could come up with any meaningful information going that route. And I believe, yep, that, Randy, is my last slide that I have.